lesson, you will state Newton's second law of motion, both in words and mathematically. You will convert mass to weight and weight to mass and solve problems involving force, mass, and acceleration.
In the last program, we introduced Newton's laws of motion. We spent a lot of time on the first law. Do you remember another name for it? If you said the law of inertia, you're right. Remember that this law says that objects at rest tend to stay at rest, and objects in motion tend to stay in uniform motion. But that's true only under what condition? It's true only when there is no net force acting on the object. And what does that net mean? It means that there could be many forces acting on an object in different directions so that they add up to zero. At the very end of the last program, we introduced part of Newton's second law of motion, the law of acceleration. Do you know how this one differs from the first law? This time, there is a net force exerted on our object, and the law states that the object will accelerate in the direction of that net force. We'll always use a big fat arrow, like this one, to show the direction of the acceleration. It'll come in handy when we work problems involving several forces. But one thing is certain. The acceleration will be in the same direction as the net force, even if the object is moving in the opposite direction. Remember that acceleration describes change in motion, not the motion itself. But there's more to Newton's second law than what we told you before, and it has to do with the effects of mass and force on acceleration. To find out how these three variables are related, let's do a simple experiment. We'll use the spring-loaded exploder on this cart to exert a force on another cart. When the pin is tapped, the exploder will be released. To increase the force exerted, we'll push the rod into the second notch, compressing the spring more. To get a general idea of how much the cart accelerates, we'll measure the time it takes the cart to go from one end of the track to the other. The greater the acceleration of the cart at the beginning, the less time it will take to travel a set distance. Here's the data table for part 1 of our experiment. You do not need to copy it. We'll fill in the chart on the screen, and you can make conclusions on the spot. All we want is enough data to make a conclusion about the relationship between force exerted and acceleration. So we'll keep the mass of the cart constant, vary the force, and see what happens to acceleration. Here goes trial 1, with the exploder set to the first notch, which provides a small force. The time for trial 1 is 4.15 seconds. Now, we increase the force to be exerted on our cart for trial 2. The time for this trial is 1.41 seconds. Look at the times in our data table and make a conclusion about the relationship between the net force exerted on an object and the object's acceleration. Use the times to help you determine whether acceleration has increased or decreased. But don't include the word time in your conclusion. Tell your teacher. Now, a physics surfer would just look at this last column, see that the numbers decreased, and conclude that as force increases, acceleration decreases. But we aren't physics surfers, are we? Diving deeper into the situation, we see that as time decreases, acceleration must be increasing because the cart moves faster. This means that the acceleration of an object increases when the net force increases. If we did a more quantitative experiment, we would discover the same thing that Newton discovered. Acceleration is directly proportional to net force. Now, let's see how mass and acceleration are related. This time, we'll use the second notch of the spring exploder for both trials, keeping the force exerted on our cart constant. We can use the data from trial 1 because in it we set the exploder on the second notch. Remember that the time was 1.41 seconds for that trial. Now we'll add a heavy rider to the cart, increasing the mass. We'll keep the force constant and repeat the experiment. For this trial, the time is 1.75 seconds. Look at the data for part 2 of the lab and tell your teacher how you think mass and acceleration are related. Remember, no surfing allowed. Think about what the data tells you. If surfing led you to the wrong conclusion last time, maybe you were more careful this time. As the mass of our cart increased, it took more time for the trip. That means that acceleration decreased. So acceleration must be inversely proportional to mass. Now we can complete our statement of Newton's second law of motion.
You already have the first part of the law in your notes. When a net force is exerted on an object, the object accelerates in the direction of the net force. Now add the second part. The acceleration of the object is directly proportional to the net force exerted and inversely proportional to the mass of the object.
Now that's a lot of writing for one law, isn't it? Let's make things easy by changing our two proportions into one equation. Here it is. Since force and acceleration are on opposite sides of the equal sign, they are directly proportional. And since mass and acceleration are on the same side, they are inversely proportional. All we need to add in order to complete the law is the fact that the acceleration is in the same direction as the net force. You can add it in writing like this, or we could simply put arrows over force and acceleration in the equation, like this. It shows that both force and acceleration are vectors and must be in the same direction. So, that's Newton's second law, the law of acceleration in a nutshell. Now we need to check out the units, since they must be the same on both sides of the equation. We know that the MKS unit for mass is the kilogram, and acceleration is meters per second squared. So, in fundamental units, the unit for force is the kilogram meter per second squared. Of course, we call this derived unit by a nickname, the Newton. Let's get all this in your notes.
Mathematically, Newton's second law is stated as net force equals mass times acceleration. The arrows show that force and acceleration are vectors in the same direction. The unit for force is the Newton, which is defined as the force required to accelerate a mass of 1 kilogram, 1 meter per second squared. In fundamental units, a Newton is a kilogram meter per second squared. The dot shows that the units are multiplied.
Do you need to memorize the law? Absolutely. But that will come naturally after you use it in a few problems. Do you need to memorize the fundamental units for the Newton? No way. If you are asked for this information, just remember F equals ma. You should already know the units for mass and acceleration, so you can figure it out. Remember, don't memorize anything that you can figure out. Memorizing without thinking is just skimming the surface. No surfing allowed. Now, with every mathematical law, there comes a set of problems. So, let's dive into some second law problems. Your teacher will pause the tape and give you some easy problems to solve. The last one will be more difficult, but you can do it if you use what you already know. After everyone is finished, we'll come back and go over the problems with you.
Local teachers, please turn off the tape and give students this problem set number 1 from the Facilitator's Guide.
The first problem is a straight plug and chug. We know mass and acceleration and want to solve for net force. So we'll plug into the equation F equals ma. The force is assumed to be the net force. We use 1,400 kilograms for the mass, 1.5 meters per second squared for the acceleration, and the answer is 2,100 kilogram meter per second squared. That's a Newton. So our answer is 2,100 newtons. In the second problem, we know net force and acceleration and want to solve for the mass of the rock. We rearrange the equation F equals ma to solve for mass. Mass is force divided by acceleration. Our force is 18 newtons. Our acceleration is 17 meters per second squared. And so the mass turns out to be 1.1 kilograms. If the units bother you, remember that the Newton is a kilogram meter per second squared. So the meters per second squared would cancel out, giving you the answer of kilograms. If you use the MKS system units throughout the problem, your units will come out correctly. So don't worry about that. Number 3 is a two-step problem, but each step should be familiar to you. Let's look at it. We have a constant net force of 870 newtons applied to a mass of 310 kilograms. We want to know how far the motorcycle will travel in the first 16 seconds, starting from rest. So we have lots of information. The trick to solving this kind of problem is recognizing the fact that you will need 2 steps and 2 different equations. Now the trick to really help you is to divide your data and your problems. Put F equals ma data on one side, put acceleration equation data on the other side. Let's look. We have 870 newtons. That's our net force. Mass also belongs over here. That's 310 kilograms. How far? We want to solve for D. We know that our time is 16 seconds, and we're starting from rest. So initial velocity is equal to 0. Now, look over here. If you have 2 out of 3 variables, you can solve for the third. And that will come in really handy because you cannot solve an acceleration equation without involving acceleration, and we don't know the value of A. So we'll find it out over here. A will be F divided by m, or 870 newtons divided by 310 kilograms. The value of A turns out to be 2.8 meters per second squared. Just because you have an answer, don't think you're finished. We want to solve for how far the motorcycle will travel. So we'll simply put the value of A over here. Now we want an equation starting from rest that involves D, T, and A. And you should recognize that it's equation number 2 and that we don't even have to rearrange. So we get 1/2 times 2.8 meters per second squared times 16 seconds. Don't forget to square that. The answer, rounded to 2 significant digits, is 360 meters.
Always reread a problem before you leave it to be sure that you've answered the question. Sometimes you can get so involved in the first step that you'll go on after you get that first answer, and you'll regret it later. Now, look at this problem. Don't copy it. Just decide whether you have enough information to solve it or not. Can you solve it in your head? If you multiplied 48 times 3.0, and got an answer of 140 newtons, you are indeed a physics surfer, and a wrong one at that. Look at the problem again. Is 48 newtons the mass of the bowling ball? The newton is not a unit of mass. It's a unit of force. Let's look at the diagram of the forces acting on the ball. The weight of the ball is the force of gravity pulling the ball straight down. But the floor pushes upward on the ball, supporting it. These two forces cancel out, so there is no net force acting on the ball in a vertical direction. Because the bowler pushes the ball forward across the floor, the net force acting on the ball is horizontal, and the acceleration will be in that same direction. So we can't use the weight of the ball as a force in this problem. What we need is the mass of the ball. How can we find it? Well, that's another matter. We'll come back to this problem after we explore the relationship between mass and weight. It turns out that the relationship is based on Newton's second law of motion, F equals ma.
The relationship between mass and weight can be found in a special case of Newton's second law. In free fall, the net force acting on an object is the object's weight, and the acceleration will be acceleration due to gravity, or g. In most places on Earth, the value of g is 9.80 meters per second squared. So to convert mass to weight, we multiply by 9.80 meters per second squared. And to convert weight to mass, we rearrange the equation and divide by 9.80 meters per second squared. It's as simple as that.
Do you have another equation to memorize? No. It's still F equals ma. Just remember that when weight and mass are involved, A becomes G. And you've done enough work with G to know that its value is 9.80 meters per second squared. Your local teacher is going to put this problem set on the board for you to copy and work. When you are finished, we'll go over the answers.
Local teachers, please turn off the tape and give students this problem set number 2 from the Facilitator's Guide.
Here are the answers to the problems you worked. For number 1, you simply multiply the mass times 9.8 meters per second squared, because weight equals mass times our special case of acceleration, which is g. That gives us weights of 18,000 newtons for A and 1.2 newtons for B. In number 2, we rearrange Newton's second law to solve for mass, and we get weight divided by g. So we will simply divide by 9.8 meters per second squared. That gives us 1.4 kilograms for A and 69 kilograms for B. Now let's look at number 3. On Earth, 75 kilograms is equal to 740 newtons, rounded to 2 significant digits. On the Moon, we use 1.6 meters per second squared as the value of g. That gives us a weight of 120 newtons. Remember that mass does not change, but weight depends on the force of gravity or the value of g. I think we're ready to go back to our bowling ball problem now, don't you? When you read a problem, make a list of data and pay attention to the units. Remember, we want no naked numbers. We want to solve for net force. And we know acceleration and weight. But to use F equals ma, we need mass, not weight. So we'll quickly convert our 48 newtons into mass by dividing by 9.8 meters per second squared. You don't even have to do the math. In fact, it's probably better if you just leave it as mass equals 48 newtons divided by 9.8 meters per second squared and plug and chug. Now we're ready. Net force will equal 48 newtons divided by 9.8 meters per second squared times 3.0 meters per second squared. Our answer is 15 newtons.
Try this one. Your teacher will pause the tape and give you the problem and enough time to work it. Then, we'll come back and go over the solution. Remember to watch your units.
Let's start with Part A. We're given the net force and asked to find the ball's acceleration. Anytime you're given acceleration and net force, look for a way to use F equals ma. All we need is the mass, but we have the weight of the ball. That should not be a problem. You should know that mass is weight divided by g. So that's 1.1 newtons divided by 9.8 meters per second squared, giving us a mass of 0.11 kilograms. Now all we have to do, solve for acceleration, which would be net force divided by mass. Our force is 19 newtons. Our mass is 0.11 kilograms. And our answer is that the acceleration is 170 meters per second squared. Did you realize that a baseball accelerates that fast? Well, it does. Now for Part B. You should recognize this one as an acceleration problem because we have starting at rest, moving so far. We want to know the speed that the ball has when it leaves the pitcher's hand. And so we'll jot these down. Our displacement is 3.3 meters. We're starting at rest, so initial velocity is 0. We want to know the final velocity, and we're going to have to know the acceleration. We can't solve an acceleration problem without acceleration, so we'll use the answer to Part A and put it here, 170 meters per second squared. Now, which equation will we use? Look in your notes for the three equations, and you will see that number 3 fits what we need. Final velocity squared equals, initial velocity is 0, so we'll simplify it. It equals 2AD. We'll take the square root of both sides. Our final velocity will be the square root of 2 times 170 meters per second squared times the distance of 3.3 meters, which is about the distance from this position to the full out extended position. And our answer is 33 meters per second. That's about 74 miles per hour, so it's not a fastball in the major leagues.
It's time to try some problems like this one and the one with the bowling ball on your own. Your teacher has some practice problems for you. Pay attention to the units and separate your data if the problem involves more than one step. You'll go over the solutions in your class and then have a quiz. When we come back, you'll finally find out why this bowling ball and this marble would fall at the same rate in an airless environment. So, practice your problem solving, and I'll go bowling. See you later. It's time to show what you know. Jot down your answers. Your local teacher will go over the answers with you when the program is finished.
Question number 1 is, Newton's second law of motion is also known as the law of A, inertia, B, action-reaction, C, acceleration, D, gravity.
Question number 2 is, the acceleration of an object is inversely proportional to A, the net force acting on it, B, its mass, C, its weight.
Question number 3 is, to complete the statement of Newton's second law, we need to add this to the equation F sub net equals m times A. A, net force and acceleration must be in the same direction. B, arrows in the same direction over the F and the A. C, either A or B.
Question number 4 is, what is the mass of an object weighing 4 newtons? A, 4 newtons times 9.80 meters per second squared. B, 4 newtons divided by 9.80 meters per second squared.